Chapter 8 Review. Number 1 asks you for the 4 indications of a chemical reaction. So I want you to think back to the lab that we did because it had some of those chemical reactions. Here are 4 of the things that we saw in the lab: changes in energy, which we would see as change in heat or the production of light. So obviously when we burn the magnesium, we saw a bright light. If things get hotter or colder, that is also an example of that. The second example could be a color change, and that is if something was clear and it changed to colored. In the case of when we put the aluminum into the copper 2 chloride, that changed colors as the aluminum was dissolved and the copper came out of the solution. The production of a gas, we're going to see that as bubbles. When we put the zinc in the HCl, it definitely bubbled, and then we collected the gas, so that's another way. And then the last way we're going to talk about is the formation of a solid or a precipitate. The example of that was the very last thing we did in the lab when we mixed the sodium chloride and the silver nitrate, and we mixed those together, and we got a white milky looking substance. But if you looked really closely, or if you let it sit for a little bit, you would see that that was actually a white solid in there. So question number 2 asks us, why do we balance equations? And that is because we have to satisfy or obey the law of conservation of mass. So if we start with 4 atoms of chlorine, we better end with 4 atoms of chlorine. If we start with 40 grams of reactants, we have to end with 40 grams. And so if we do not balance the equation, then the law of conservation of mass is not satisfied, and it is not correct. It says, how do we balance equations? And I've written this really big to get it through everybody's heads. We use coefficients in front of the correctly written formulas. Once we have a formula written correctly, we do not ever change the subscripts. And I've caught some of you doing this, and it's not correct. When you change the subscripts, you change the formula. So we only use the big coefficients, the big numbers in front, to balance equations. Okay, so let's practice balancing some of these equations. We're going to start with this first one right here. So I have 1 iron here, 1 iron here. 2 chlorine, 3 chlorine. So because I have 2 and 3, I'm going to have to balance that. And the best way to do that is make that be a 6 on both sides. So to make this chlorine be 6, we're going to put a 3. And to make this chlorine be 6, we're going to put a 2 in front of it. And then we look and see what that did to our iron. It gave us 2 irons right here. And since we only have 1 right here, we're going to have to put a 2 there. In the next equation, that's a combustion. We want to look first, remember when we're doing combustions, we want to look first right here at this hydrogen and balance it first. And to have 16 hydrogen on both sides, I would need to put an 8 there. Because that's an even number, we're going to be good to go, so we're going to put an 8. Then I look at my carbon, and I see that I have 7 carbon here and only 1 there. So we're going to easily fix that by putting a 7 in front of CO2. Now I'm going to look at my total oxygen content and balance oxygen last. Okay, so here I have 7 times 2, which is 14. And then I have 8, so 14 plus 8 is 22. So since I have 22 total oxygen on the product side, I need to do 22 on this side. So that's easily done by putting an 11 in front. And then I can do a double check and make sure that everything is the same on both sides, and it is. On our next one, we have aluminum sulfate plus calcium hydroxide, which is going to give us aluminum hydroxide and calcium sulfate. So we're going to start with, let's start with the metals. Okay, so right here I have 2 aluminum, and I only have 1 here. So I'm going to put a 2 right there. Okay, and remember when we're doing these types of problems that have these polyatomic ions like here and here, we're going to treat those as all one unit. And so instead of breaking them up into their individual components, and that makes it easier. So the next thing that I notice is right here I have 3 sulfates, and I only have 1 sulfate over here. So I can fix that by putting a 3 in front of calcium sulfate. And then I notice that now I have 3 calcium and I only have 1 calcium here. So I'm going to put 3 right here in front of calcium hydroxide. And when I did that, it also helped take care of my hydroxides. 3 times 2 is 6 hydroxides. 2 times 3 is 6 hydroxides. And now everything is balanced. So we have one more to look at. We have the decomposition of potassium chlorates going into potassium chloride and oxygen. My potassium and chlorine are balanced as is, but my oxygen is not. I have 3 and 2. And anytime I have 3 and 2, I want to make them be a total of 6 on both sides. So to make this side be 6, I'm going to put a 2 in front of there. To make this side be 6, this oxygen be 6, I'm going to put a 3 there. And then, of course, when I do that, it gives me 2 of the KCl and only 1 here, which is easily fixed by putting a 2 in front of there. So in this one, it asks you to write the notation for a chemical reaction indicating the states of matter. And we can do any reaction that we want to here. It doesn't really matter, but we're going to use the one that we did in the lab where we put the zinc inside of the HCl and it bubbled and we produced a gas. So here we have zinc, which is a solid, and 2HCl, which was aqueous. And then when it bubbled together, if we would have let it go all the way, we would have gotten zinc chloride, which is aqueous. And then, of course, hydrogen we know was a gas that we collected in the test tube. The one that it's not listed on here is if something is a liquid. And, of course, if something is a liquid, we would indicate that with a L. Number 6 is asking how do we correctly represent diatomic elements. And of course I've been drilling this into your head. Diatomics are your Brinkelhoffs, which are written with the little 2's underneath them because they exist like that when they are by themselves. Remember, only when by themselves, not when they are in a compound. Only when by themselves are they written this way. All right, question 7 asks how is a catalyst indicated in a chemical reaction? First of all, let's talk about what a catalyst is. A catalyst is something that speeds up a reaction, but it is not a part of the reaction. In biology, example of that are enzymes. We have enzymes in our body that help the reactions along in our body. In chemistry, we call them catalysts. But the way that we indicate a catalyst is we write it above the arrow, above the yield arrow, when we're showing that a catalyst was involved. But this catalyst is not used up in any way. It's just there to help speed up or give it an alternate pathway. All right, what is electrolysis? Electrolysis is essentially decomposition by electricity. And here's an example of how we would show that. Again, it's not part of the reaction, so we put it above the arrow. Another thing that we saw on some of our homework is sometimes we'll see an arrow with this little symbol above it. That means heat. So that's another thing that we can see. But this is an example of decomposing water by running an electric current through it, and it will break it back down into oxygen and hydrogen. So here we're going to indicate what type of reaction it is and go ahead and practice balancing those equations. And so when I look at this first one, I see that I have a compound plus a compound. And anytime I have a compound plus a compound, that means I have a double replacement reaction. And remember what happened here is our outside things went together and our inside things went together. And so when I do that, I look at that and I get lead nitrate and silver chloride. I need to balance that. And so I'm going to do that. I have 2 nitrates right here. And so I'm going to put 2 nitrates right there. By doing that, that gave me 2 silver. And so I'm going to put 2 silver right there. And then that also took care of my chlorine. So now that would be balanced. Just for practice, we're going to look real quickly at our solubilities of these. We know that nitrates are always soluble. So we can go ahead and say that that one would be AQ. And if we look at chlorides, they're soluble unless they are with one of those heavy metals, which happens to be silver. So this would actually be the solid in that case. The next reaction, I see that I have only one product. And whenever I only have one product, that means that I have a synthesis reaction. And if I look at that, I see that I have 1 nitrogen here, 1 nitrogen here, 1 hydrogen, plus this one is 4 total hydrogens, 4 here, and then 1 chlorine. So that one is already self-balanced. Okay, 3 more here. So very quickly again, I see that I have a compound and a compound, so that one's going to be a double replacement. Let's balance that real quickly. I see, first of all, that I have 3 sulfates right here. So I'm going to go ahead and throw down 3 right there. And I see that I have 2 aluminums and I only have 1 over there. So let's do that. And then let's look at either sodium or chlorine, either way. Both of them give me 6 chlorine on right here, 6 chlorine right here, and 6 sodium right there. So that's going to easily be fixed by putting a 6 right there. So now that would be balanced. I look at the next one and I see that I have an element plus a compound, and it's producing an element plus a compound. And anytime I have element plus a compound, that means I have single replacement. And then if I look at that, I see that that one is actually already self-balanced because I have 1 iron on both sides, I have 2 hydrogens on both sides, and then I have, excuse me, 1 sulfate on each side. So that one is already balanced. And then lastly, I look at this one, and this is that funny little hydrocarbon. And so anytime I see hydrocarbon plus oxygen, always yielding CO2 and water, I'm going to know that that is, in fact, a combustion. So let's practice balancing that. I look right here. I have 12, excuse me, I have 12 hydrogen, which means I'm going to need to put a 6 right here. Since that is an even number, I don't have to worry about bumping anything up, so I can put my 6. And then I have 4 carbon right there, so I'm going to need to put a 4 right there. And now I do my total oxygen content, so I have 8 plus 6 is 14, so I'm going to put a 7 right there. This reaction, we have potassium hydroxide plus phosphoric acid. So when we see that, we know that hydroxides are bases, and of course we know this is an acid. So remember, anytime we have acid plus base, we get an ionic compound and we get water. Okay, so just like on our double replacements, we get outside and inside going together. And so our acid is going to give us a hydrogen, and our hydroxide is going to come from the base, and that's going to make our water. And remember, when we make this, remember to think of this as HOH, so we know how that went together. And then what's going to be left is potassium and phosphate. We still have to put those together based on their charges. Potassium is a +1 in a charge, and phosphate is a -3. So that would be K3PO4. And remember, this is going to be liquid water because it's pure. And then because potassium is always, group 1 metal, always soluble, it's going to be aqueous. And so now we have to worry about balancing those. And so when I look at that, I see that I have 3 potassium right here. And so I'm going to need to put a 3 in front of there. And then when I do that, I'm going to look at my total oxygen here. And I see that I have 3 plus 3 is 6 total hydrogen on this side of the reactants. And so I'm going to need to put a 3 right there. And then when I do that 3, it also took care of my 3 oxygen and 3 oxygen here. So now it is balanced. For a metal A to replace metal B, it must be above or below metal B. And of course, that's going to have to need to be above it on the activity series. Remember, the top is the most reactive. It can replace anything below it, but the bottom is the least reactive, and it cannot replace anything that comes above it. So last part, let's predict what it's going to make. And so this first one is a single replacement. So we need to ask ourselves, will aluminum replace magnesium? So we look at our activity series and it will not. So this one would actually be no reaction. That would not happen. And so then we're going to look at this next one, which is also a single replacement. And we want to see, will hydrogen replace copper? And it will, because hydrogen is above it. So it's going to kick copper out and join with chlorine. Based on their charges, hydrogen a +1, chlorine a -1, we would form an HCl. And then, of course, when we kick copper out, anytime we write a metal by itself, it's just the symbol, and that's it. And then we would have to go back and balance this. 2 hydrogen and 2 chlorine is easily fixed by putting a 2 right there. All right. The next one, also a single replacement. So we would look at the activities in series and see, will lithium replace hydrogen? And of course it will, because lithium is at the top of the list, so it replaces everything. So it's going to kick hydrogen out. by itself as in the form of a gas. And of course, when hydrogen's by itself, it's one of our diatomic Brinkelhoffs, so it's going to be H2. And then we're going to join up lithium and chlorine. Lithium is a +1 in a compound, chlorine's a -1, so it goes together as LiCl. But this is obviously not balanced because I have 2 hydrogen over there on the product side all by themselves. So I'm going to put a 2 right here, and then of course that throws everything out of whack, so I'm going to need to put a 2 and a 2, and now it is balanced. And then this last one, double replacement. So we're going to do outside and inside things together. So I'm going to put potassium and nitrate. Potassium +1, nitrate -1. So it's a KNO3. And then I'm going to have lead. I have lead 2 here since I had 2 nitrates, and chlorine. So that's going to be PbCl2. Because that is a double replacement, we need to now go look at our solubility rules. Potassium, group 1 metal, always soluble, so it's going to be aqueous. Incidentally, nitrates are always soluble, so it's also, because of that, going to be always aqueous. Remember, soluble means stays dissolved, so that means it's aqueous. Now we go look at chlorine, and when we look at the chlorines, it says chlorines are soluble unless they are with one of those heavy metals, lead, silver, and mercury. So since we have one of those, it's going to be insoluble, which means it's going to make a solid. So now we need to go back and balance. So I see that I have 2 chlorine and 2 chlorine, so I'm going to need to put a 2 there. 2 nitrate and only 1 nitrate, 2 potassium, so I'm going to need to put a 2 here, and so now everything is balanced. So, what should you study for the test? You should definitely study your notes. Remember, you will have available to you the activity series, an ion list, and your solubility rules. But you are going to need to learn and memorize some of those things on the blue sheet, which is your types of reactions. The test is multiple choice and some free response, and so you need to definitely look over your notes. If you haven't read the chapter, we always highly suggest you read the chapter. You don't always listen, but we do recommend it. All right, my jokes this time come from the courtesy of 2 of our students. First one is second period, Joel Trevino. He asked, what happens when salt kills pepper? He's charged with assault. Second joke comes from 6th period, courtesy of Samuel. And he asked, what is worse than raining cats and dogs? Hailing taxis. All right. Have a good night.